Okay, so in this video we're going to go over how the handheld unit actually calculates the rocket trajectory. What comes in from the SD card into the system is the rocket, the name, the mass, and the cross-sectional area of the rocket. So the rocket has a cross-sectional area of the tube plus the leading edge of the fins, and that gets loaded in to the simulation. From the engine section, we get the engine name, the propellant mass, the casing mass, the thrust at each 1/100th of a second. And you can actually see that when we load up into the engine menu, you'll see a thrust curve, and that's actually pulling from the card to show you what the thrust will be at each 1/100th of a second interval. The program runs by taking a snapshot every 1/100th of a second and running this series of calculations and then feeding the answer into the next step of the simulation. The initial conditions start with the rocket on the pad. In the settings, we know what the rocket launch rod length is, so we know how long it's going to be accelerating on a certain path. And the initial flight path angle is the angle between vertical and going towards horizontal. So maybe from 0 degrees to about 20 degrees, typically. So each step of the simulation will calculate the net forces on the rocket each 1/100th of a second. So we have drag force off the bottom, the gravity force pulling down, and the thrust force pushing the rocket always opposite to drag. And for my simulation, I always assume that drag and thrust are always opposite each other, just because in order to create a drag vector that would not be in line with the thrust vector, we would need to know the center of gravity, and we'd have to use integral calculus to calculate the center of pressure at every moment in time. It would just make this simulation so much more complicated than it already is. And honestly, the results probably wouldn't be all that much more accurate, especially since we have a plus or minus 10% burn on the engine. We don't exactly know which direction and speed the wind is blowing from. We don't know the frictional forces on the launch lug as it leaves the pad, and other things like that. But for this simulation, we'll calculate the drag force first, and the drag force is 1/2 rho, which is the air density, v squared of the rocket, velocity squared, the coefficient of drag times the area. And we have sensors inside of the pad unit that actually measure the pressure and the temperature and the launch rod angle to fill in these values for this drag equation. So the rho is calculated by using a combination of temperature and pressure, and a formula that I wrote within the program for that. V squared is carried in from the previous cycle of the program. Like I said, each time it runs 1/100th of a second, it'll feed in what the initial velocity was at the end of the last step for the next step's calculation. The coefficient of drag is a constant for the rocket, and that's pulled in on the SD card for a given rocket. And the cross-sectional area also comes in off the card. Both of these are retroactive forces. We also have gravity, which is the mass times g. G is a constant 9.8 meters per second, and the mass of the entire rocket will be the mass of the propellant plus the mass of the engine plus the mass of the rocket itself. The thrust value, opposite the drag, is pulled in at, like I said, each interval off the card. So what the system will do to calculate the net force on the rocket, because we're going to need that for acceleration, will be the thrust, and then we'll subtract off the drag force plus the cosine of the flight path angle initial times gravity. And we use the cosine of the flight path angle because if the rocket is perfectly vertical, the cosine of 0 is 1, so gravity will be completely retroactive, combining exactly with the drag. But as we go towards 90, the gravitational force is less retroactive in the y-axis, so we have to reduce that by the cosine of that angle. If it were horizontal, the cosine of 90 is 0, and it wouldn't have any vertical retroactive effect, because gravity always works in the vertical axis. So once we have the net force, we'll need to figure out the entire mass. So that's the mass of the rocket plus the mass of the engine casing plus the mass of the propellant. Acceleration is just derived from F equals ma. So if we rearrange F equals ma, we know that force divided by mass equals acceleration. So we'll take the net force that we calculated, divide it by the mass that we calculated, and we'll also divide it by the time interval, because this would give you meters per second, but we need meters per hundredth of a second because that's our interval of our simulation. We'll then figure out, once we know our acceleration, we'll take our initial velocity, which is what we carried in from the last step, and add acceleration to that. So then we'll know our velocity for this particular step. Then we'll break our velocity vector into two components, the vertical component and the horizontal component. And the way we'll do that is we'll take for the x component of the velocity, it'll be the sine of the flight path angle initial times the velocity. And then we'll have the vertical component as the cosine of the flight path angle initial times the velocity. Then once we know what those velocities are for this particular step, we'll then recalculate our flight path angle as the flight path angle final, which is what will feed into the next step of the formula, which is what we fed in here. So this actually feeds back into this net force for the next step of the simulation. That's going to be 90 minus the arctangent of y velocity divided by x velocity. And that'll give us this angle right here. This is theta, and then we subtract 90, or 90 minus this, and then we get this angle, which will be the actual rocket. And that actually also works as it goes negative, because all the signs line up, and it'll keep track of our flight path angle throughout the entire flight. Once we know what our x and y velocity are and the final flight path angle, we can then calculate what our x displacement will be and our y displacement, and that's what we actually plot on the screen. So initial displacement plus x velocity times time for the interval will equal how far it traveled in the x direction, and initial y displacement, how high it started, plus the y velocity times time will be where it winds up in the end of this step. And the program will just put a dot at that point, and then it'll run it again, and it'll put another dot, and you'll end up getting this flight path that kind of looks like this. Now, at some point, you're going to have a burnout. The burnout is denoted by a circle, a red circle, and that happens when we reach the end of when thrust equals 0, when we reach the end of our thrust curve from the card, we assume that burnout has happened. So we put a circle there. Then we know that we're coasting for the burnout plus the delay. So when we put the delay in on the engine page, when we make it a C6-7, we know from this point we're going to coast another 7 seconds. At that point, we're going to put our parachute deployment donut. When the y component of velocity becomes 0, that's where we're going to put our apogee. So we know that the apogee is when the rocket stops rising and then starts falling again. And then at this point, when the parachute deploys, that's when our drag, our cross-sectional area actually blooms out to the size of the parachute size area plus rocket cross-sectional area, and that gives us a much larger cross-sectional area, so that the rocket will instantly stop because the drag force will become very high. So not instantly, but pretty close to instantly come to a stop, and then it's just going to start coming back on the wind. The simulation uses calculates for wind based on our x velocity. So we just subtract off our x velocity by how much the wind is. So when the rocket's x velocity is 0, we still have a negative whatever the wind speed is that will pull us back on the simulation step by step. It will also reach terminal velocity because when the drag force is equal to the gravitational force, we'll stop accelerating. So we'll have a constant y velocity pulling us down and a constant x velocity at the speed of the wind. Once the simulation reaches 0 feet, it goes negative, we mark, and that's the end of the simulation. That'll be where the aircraft actually touches down on the ground.